This is a lecture on linear programming for Math 107, Chapter 5. If you're interested in these kind of problems, there is a class up at Anchorage. It's Math 270. And in this class, all you do are linear programming, various supply and demand. You do business problems using the algebra of 107. In fact, for business majors, 270 takes the place of 107, satisfies the requirement for it, but it's a very good class. So what we've done so far is that we have solved linear equalities. Those were those linear equations. And now we're going to work with linear inequalities. These can arise in many situations, and we're looking here, of course, at business situations, and they are called constraints. Examples might be having only so much money available to start a business. Or say you're manufacturing something, but you can only get so many hours of manufacturing time. Or maybe you can only get the paint booth for so many hours. Or maybe only so many leases are available. These are all constraints on your ability to do business. Sometimes, though, you'll see these constraints in another direction. If you're planning a hospital diet, for example, you would have to have some minimum daily requirement of vitamins that you're giving these people to eat. Or if you're setting up feed for animals, there's certain requirements that the animals have, and you have to meet those minimums. Right. So those would be also constraints, although they're in a slightly different direction. Linear programming is a method where you can make some decisions based on these constraints. And this method has three parts. The first involves those constraints. You have to write them as linear inequalities. Sometimes this takes some practice. Right. Then from these constraints you develop what's called the feasibility region, and that would be a region on the graph, on a graph showing the number of different products you're going to make, the amounts that you're going to make. You'll find some region in there where you can say schedule these different combinations of products to be made, and you'll not violate any of those constraints. For example, you wouldn't schedule 40 chairs to be made if each chair took, say, 3 hours to make and you only had 60 hours of manufacturing time available. Then there's also an objective function. The objective function is an equality, and it is, generally it's the profit. And you have a goal with that objective function. Your objective is to maximize profit. Or in case you're setting up, for example, feeds for some animals, you might say, I want to minimize the cost, and you still make the proper nutrition for them. That's your objective function, and that has to be written as a mathematical equation too. So I want to talk a little bit about the constraints, and the only thing we're going to discuss here are systems with two variables. That means two products, and you have to give them some variable names of one letter is a good idea, and try to make it relate to what you're talking about. But right now I'm just going to use X and Y. Right. So we're going to make two products, product X and product Y. And there are immediately two constraints on these amounts. These are the amounts of the products you're going to make. They have to be positive. You can't make negative number of chairs, right, or a negative number of coats, for example. So X has to be greater than 0 and Y has to be greater than 0. As a result, when you start graphing things, you only have to look in quadrant 1 because of this constraint. Now I'll show you an example now of how to write the constraint for a situation. Say you were going to make tables and chairs. So I'm going to let the number of tables I make is going to be called X, and the number of chairs I make is going to be called Y. Right. Let's say it takes 5 hours to make a table and 3 hours to make a chair. But all I have available are 40 hours of manufacturing time, or that's all the time I have to work. Say I'm doing this myself, and I only have 40 hours available to work in a week. So the constraint is the number of hours. This would be the number of hours I spend making tables. That would be 5 times X, plus the number of hours I spend making chairs had better be less than 40. Okay, because I don't have any more time than that. So here, you see this is an inequality. See the less than or equal to sign here? Okay. And this is how you figure it up. X is the number of tables I make. I multiply by 5. That's the number of hours I spend making tables. Here's Y is the number of chairs I make times 3. That's the number of hours I spend making chairs. And I add all that up, and that has to be less than my constraint on time. Now I'm just going to go through an example, and I'm not going to talk about the theory behind linear programming. I will just mention it. Okay, let's say you're making wood chippers and you've got a deluxe model and an economy model. I'm going to call the deluxe model X and the economy model Y. And if when I sell a deluxe model, I get $500. When I sell the economy model, I make $350 profit. Okay, I know that. That's going to go into my objective function. But here's the manufacturing constraints. The deluxe model requires 3 hours to assemble and a half hour to paint. The economy model requires only 2 hours to assemble, but it requires 1 hour to paint. And the number of assembly hours I have per day is 24. So I can only get enough people for 24 hours of assembly time a day. The painting is restricted to 8 per day. And my goal is to maximize this profit. I want to maximize this. So in step 1, I'm going to write the equations for the constraints and the objective function. First I have to assign variables. D and E would have been better, but I'm going to go ahead and use X and Y. X for deluxe and Y for economy models. Now I know there cannot be a number, I can't make a negative number of wood chippers, so these two, X and Y, must be greater than or equal to 0. Remember, X is the number that I'm going to make, and Y is the number of economy models that I'm going to make. Now what is the constraint on assembly time? It takes me 3 hours to assemble a deluxe one, so 3x is the number of hours I spent assembling the deluxe model. And the economy model required 2 hours to assemble, so 2y is the number of hours I spent assembling the economy model, and I'm constrained to be 24 for the assembly time. So here's the equation for that constraint. 3x plus 2y is less than or equal to 24. Now for the painting, it took half an hour to paint the deluxe one, so for every deluxe I make, I multiply it by 0.05. That will give me, I'm going to spend half an hour painting each one. So 0.5 times x is the number of hours I spend painting the deluxe model. And the economy one took an hour to paint. So 1 times y, just y, is the number of hours that I spend painting the economy models, and I was constrained to 8 hours of painting time. So there's my constraints. You can see here I have 4 of them. I'll clear the screen. So I've got 4 constraints. I have these 2, just because I can't make negative anything. And then I have a constraint on the assembly time, and I have a constraint on the painting time. You might have even more constraints, and that's okay, but we're only going to talk about 2 items, but just for simplicity we'll leave it. This is the number of constraints. Now the objective function was to maximize profit. So my profit is going to be 500 times x, because it's $500 profit for every deluxe one I make and sell, and 350 for every economy one that I sell. So there's my objective function. You see that has an equal sign in it, because that's the profit. The others are inequalities. And now I construct a graph of the feasibility region. It's easier to see this than to explain it. So, but here's how you do it. You find the X and Y-intercepts for both constraints. In this case, we only had 2 constraints, so you find the X and Y-intercepts. It's important to find the X and Y-intercepts and not to just draw this line. You need those 2 numbers, and they're pretty easy to obtain. The X-intercept set Y equal to 0, and you find that X is 8. Here you set X equal to 0, and you find that Y is 12. That's for your constraint on assembly time. Ooh, this was a constraint on painting. Okay. So here was the equation for the inequality for the paint. Find the X-intercept by setting Y equal to 0. Find the Y-intercept by setting X equal to 0. And now I use these values to draw in those lines. Remember, they're going to be straight lines because they're linear, and all you need is 2 points to draw them. we're going to need one more point, but you don't have to see if you need this point until you've drawn the graph. There's a homework problem where the lines never cross, or at least they don't cross in the first quadrant, so you don't need to find this. But say you needed to find the place where they crossed, you would make those two inequalities equalities, and you would solve them as a system. The system's easy to solve. X equals 4 and y equals 6. You could use matrices and Gauss-Jordan. You could use substitution or elimination to solve them. It's just a system of linear equations. And now I graph all this information and determine the feasibility region. Okay, here I've graphed those lines for the inequalities. I've graphed the inequalities in quadrant 1. Remember, I only need to look at quadrant 1. So the blue line was the constraint on my paint. I'm painting. The red line is a constraint on the assembly time. And if you remember the corners, which you might not, the X and Y-intercepts for the paint, here, this was the Y-intercept, here was the X-intercept, and for the assembly, here was the Y-intercept, I'm sorry, and here's the X-intercept. Okay. Anything that I schedule that's less than this line will get done in terms of assembly. Anything less than the red line, and I've shaded that in red. Anything less than this blue line, which shaded over here in this region, any combinations of, this is X and this is Y, will get painted. For example, if I schedule 10 deluxe models and 2 economy models, that would put me right there, and I would have enough painting time to get those done. If I schedule 2 deluxe models and 10, I think that makes it, may say 1 deluxe model and 10 economy models, I'd have time to get that assembled. But the feasibility region is the region where both the painting and the assembly would get done. So that's a double-crossed region, and that's in here. So for example, if I schedule 4 economy and 4 deluxe, then those, I can be assured that that many models will both get assembled and painted. Now there's some points that are very important here, and those are called the corners of the feasibility region, and we found those by those X and Y-intercepts. 0, 0, of course, is a corner, although for problems of maximizing profit, it doesn't offer much. Then here's the other one, right here. Here's another corner down here, and the point where they cross make a corner. This Y-intercept lies outside of the feasibility region, so you can ignore it. Same with this X-intercept. Now the theorem of linear programming says that the objective function will be maximized or minimized at one of the corners of the feasibility region, or if it is the same, say it has the same value at 2 corners, it will be along this line of the feasibility region, along this border, the boundary of the feasibility region. So it's going to be maximized at one of these corners of the feasibility region. So what we do is you take that objective function and we evaluate it at these corners and see where it's maximum. So here are the corners in a list, and here is the objective function P, which you didn't remember what P was. 500x, that was $500 for selling every deluxe one, and $350 for every economy one. Okay, so I put, in this case, x of 0, y of 8 into the equation, and I say that if I made no deluxe models and 8 economy models, everything would get assembled and everything would get painted, and I would, within the allotted times, but the profit would be $2,800. I could pick this other combination of 4 and 6, 4 deluxe and 6 economy. Everything would get assembled, everything would get painted, and I would make $4,100. Or I could try this third corner, 8 and 0, and make $4,000. Of course, obviously this is what you want to do, because you would maximize your profit. And I've added that information to the graph. So here's a corner, this one of these corners, 0, 8. The profit here would be $2,800. This one was 4 and 6, and the profit's $4,100. And down here, no economy, and 8 deluxe models would give me a profit of $4,000. And that's a procedure. Of course, 0, 0, that of course has profit of 0. And you can pretty much disregard that, but I'll list it there for completion. So here are your problems to these linear programming problems. First, you have constraints that are based on the reality of doing business, and you have to write those out in some kind of mathematical form. Second, you have an objective function, and that is usually your profit or sometimes your cost. And your objective will be, if it's profit, will be to maximize profit. From the constraint equations, you evaluate the X and Y-intercepts and any intersections of the constraints, and from that you draw a graph and find the feasibility region. From the feasibility region, you sort out the relevant X and Y axis intercepts, and those are the corners of the feasibility region. Then you take your objective function and you evaluate it at the corners. And where it's maximum, that's the number of products that you want to make to maximize your function and still remain within your constraints.